Okay, now we'll go ahead and get started. Today we're having our seminar with Dr. Jeffress from the University of Texas A&M, Corpus Christi. Dr. Jeffress is a professor of Geographic Information Science and director of the Conrad Blucher Institute for Surveying Sciences. He's a registered professional land surveyor in Texas, Maine, and Australia. Dr. Jeffress has been one of the original co-principal investigators of the Texas Coastal Ocean Observing Network since '91. And he held the Blucher Chair of Excellence in Surveying from '90 to '91. He's held teaching positions in Australia and the US, as well as having taught short courses in Haiti. He continues in the collection and analysis of geographic data and information that will result in the sound environmental and economically viable land management and development. His research interests incorporate GIS and digital surveying applications in environmental management, land tilling, and land administration. Titling? Oh. Sure, my bad. Land titling. And without further ado, Dr. Jeffress.
Thank you. Thank you, Scott. Very much appreciate the invitation to come and speak to you today. What's not mentioned in that little bio is that I'm originally from Australia. I grew up in Sydney and got my undergrad and master's degrees in surveying at the University of New South Wales. And took a fateful trip in 1987 where I met my wife, who's from Pennsylvania, in Greece, and went to a conference in Madison, Wisconsin, where I met some faculty from the University of Maine in surveying engineering, and they invited me to Maine to do my PhD. That's where I got my PhD, in surveying engineering. So I'm traditionally a land surveyor, but I got hired by what was then Corpus Christi State University to start a 4-year degree in land surveying back in 1990 when I was finishing up my PhD. And so I went down there to start a degree program, an undergraduate degree program, because they accepted an endowment from this guy, Conrad Blucher, who was a county surveyor and married late in life. And he was the last of 3 generations of South Texas surveyors. All 3 of them were county surveyors. His grandfather, whose name was Felix von Blucher, immigrated from Berlin back in 1849 and logged into Corpus Christi. Turns out his great uncle was Field Marshal von Blucher, who led the Prussian army against Napoleon at the Battle of Waterloo. So that's our little brush with fame. So Conrad wanted to perpetuate the family name with surveying, so he left his estate to the university to foster surveying education. So I was hired to start a surveying degree. But we didn't call it surveying, we called it Geographic Information Science. Because if you start a surveying program, no one will come. Because the public doesn't know what surveyors do. So we decided to get around that by calling it Geographic Information Science, with an emphasis in surveying, which we ended up calling geomatics, and an emphasis in geographic information systems. So we teach kind of like both of those disciplines. There's a lot of overlap. And the name has actually worked out pretty well in attracting students into our program. We probably have the largest surveying program, if you want to call it that, in the United States. We have about 82 undergrads right now, and we have a master's program in geospatial surveying engineering, and that has about 30 students in it. And we just received permission from the Texas Higher Education Coordinating Board to introduce a PhD program in what we're calling geospatial computing sciences. And so I believe it's the first in the nation. So what we're focused on is the computer science specifically related to geospatial data collection and analysis, kind of like what we all do. Everything we do in the geospatial world now is digital, including all our measurements and how we display that data and analyze it and produce it to the public. So our philosophy is those with the best software win. So we're going to try to push the envelope in the geospatial arena. So I'm going to talk about the Texas Coastal Ocean Observation Network, which we started back even before I got there, back in like 1988, 89. And we've also working with the National Geodetic Survey in a program called Height Modernization, which is to update elevations in the United States, the infrastructure for elevations. So I'll talk a little bit about that as well and how it's integrated. And part of the Blucher Institute is we set up through the Texas legislature, a Texas Spatial Reference Center, which is kind of like a branch office of the National Geodetic Survey for Texas, where we help the state establish geodetic control for surveying and mapping. And so a lot of the work we're doing in the height modernization is through the Texas Spatial Reference Center. So this is where we're located. Texas A&M University has its own island campus. Down at the bottom of the screen there, it's about 120 acres, and it's getting pretty crowded. We grow at about 500 students a year. We're up to a little over 11,000 students now. And the city's just recently given us a whole bunch of real estate over here, which doubles the size of our campus. So we're growing. So the philosophy is going to leave all the academics and research on the island, and all the sports and non-academic stuff is going to go to the new campus. And this is a golf course which abuts the new campus, and looks like we'll take that over one of these days too. So we're the only campus in the A&M system that's actually in a metropolitan area. It says downtown Corpus Christi and the port of Corpus Christi, which is now the 5th largest port in terms of tonnage of cargo in and out in the nation. And you'll see from this photograph that we're vertically challenged. Our campus, if you look at the USGS quad sheet for our campus, the highest elevation is actually where the Blucher Institute building, which is right there, is 17 feet above mean sea level in 1929. It's sea level's a little higher than that now, so we'll talk about that in a minute too. But the topography has been shaped by previous ocean coverage, and also the fact that it's in a hurricane area. So a lot of things, it's pretty flat and vulnerable to storm surges. The campus, the history of the campus was started in 1947 after it was a naval base. The Navy left. It was actually where they did a lot of radar research in the Second World War, and the Navy didn't want it anymore, so a Baptist community bought it and started a Baptist college. Well, it was wiped out by a hurricane in 1970, and they couldn't afford to rebuild it, so the city bought it and then gave it to the state to start a state university. So, and then we joined the A&M system in like 1994, and that's what we are now. It's a pretty pretty campus, and we haven't had a hurricane since the 1970s. We've been pretty lucky. But a lot of things we do are based around the fact that we'll probably get one of these days. So we got into the water level business back in about 1989, specifically sponsored by the Texas General Land Office. The Texas General Land Office is the custodian for state land in Texas, and it's actually been in existence since the Republic of Texas was formed. It was one of the constitutional institutions from the beginning, and has an elected official as its head. And the elected official just changed hands was it last Tuesday or the Tuesday before last? And our new commissioner is a guy by the name of George P. Bush. Does that ring a bell? Anyway, so we have new leadership in that agency, but that agency is governed with protecting state lands, and one of the things that they're in court over is the location of the littoral boundary. That's the legal boundary between privately owned upland and the state-owned submerged land. And so why is that a big deal? Because underneath all this is oil and gas. And so the TCOM started in 1989 as a result of a court case where the state was being sued by a foundation which inherited a large ranch south of Corpus Christi called the Kennedy Ranch. And it was inherited by the Catholic Church, who set up this foundation. And adjacent to this ranch was like 30,000 acres of mudflats in that water body called the Laguna Madre. And the foundation decided to sue the state for ownership of those mudflats, as the original grants called for their eastern boundary to be the shores of the Laguna Madre. So the shore of the Laguna Madre under then was Mexican land grant, was a definition of, which was associated with what's called the Las Siete Partidas, the 7 parts of Spanish law that was written down in the 13th century, which stated that the shore was that part of the sea that's covered by the sea, be it in winter or summer, the highest extent it would go. And to me that sounds like the highest of the high tides. But there was a court case over that boundary back in 1958 in Texas called the Lutz case, and the court decided then that the only way you can determine a littoral boundary is using tide gauges, and for a Spanish land grant, a civil law grant, that was the mean high water mark, and for English common law grants, and Texas, the Republic of Texas adopted English common law back in March of 1840. So all grants after 1840, the littoral boundary is mean high water, and before that it's mean higher high water. And I see there's not much difference between the two. This is in feet, so 0.04 of a foot difference is different. It's very difficult to put that on the ground. But where these datums intersect the shore, that's where the legal boundary is. Anyway, that case was fairly interesting because all the evidence showed that these mudflats, and by the way, the original land grant stated that the land was going to be used for pasture to raise cattle. And if you're going to raise cattle, you wouldn't want 30,000 acres of mudflats in your grant. And so we started establishing these NOAA technology tide gauges, and for the fact that the data was going to go into court, it needed to be of a certain standard, and of course NOAA sets the standard. And so we followed every procedure, all the equipment, all the calibrations, all the processes that co-ops uses for their tide gauges, we duplicated and established these water level gauges. So what we're actually trying to do is produce these water level datums. Mean high water, mean sea level, and the mean low waters. And of course this is very useful for nautical charting, right? You want to know that's the datum for nautical charts. But so we've also connected to the North American vertical datum of 1988 for all our tide gauges as well. And the network is sponsored not only by the Texas General Land Office, but also the Texas Water Development Board. And that's an agency that looks after the fresh water in Texas. And a lot of that's mandated to be put into freshwater inflows into the bays and estuaries to keep them pristine. And so they do a lot of circulation studies. So they needed the data, so they've helped pay for it. And also around about 1996, the US Army Corps of Engineers started to fund it as well because they needed the data for dredging and coastal engineering projects. And so we have 3 major sponsors that fund this network. But this is what we're aiming at. And you notice, I don't know if you study the tides in any of your courses here. The tidal datums are based on an epoch. And this is down in the bottom left-hand corner. The latest epoch, which is actually set by Congress, this is another thing we follow at NOAA. It's 19 years worth of data to establish these datums, and the latest epoch was the period from 1983 to 2001. So Texas is one of the places in the United States where not only do we see sea level rise, but we also see a lot of subsidence at the same time. So we have some serious water level change going on in Texas. And so that's another reason why we monitor it, is to keep track of that. And actually, but NOAA's done a better job than we have, because they've been around longer. So that's one of the things we look at, is sea level rise. And this is some examples of sea level rise. So probably something guys don't worry about around here, but this is at Seavey Island in Maine. I think that station's discontinued, but this is the long-term record there. And it shows a sea level rise of 1.76 millimeters per year, which is not much. Actually, it's lower than the world rates. So there's probably some isostatic rebound going in to compensate for some of the sea level rise up here. Not a lot, so nothing to worry about. Another local one is in Boston, a little bit more there. This is closer to the global rate. The global rate, I'll show you in a minute, it's about 3 millimeters a year. It's about 2.8 millimeters a year, but there's a linear increase going on in Boston. And you know, this is a very long-term record here. By the way, and this is sea level with all the known cyclic parameters taken out, you know, like the daily tides and the annual cycles and all the lunar cycles have all been modeled out. And you still get this very noisy signal. And that's one of the things that we'd like to look at, is what's causing this noise. Because right now, the water level experts around the world reckon that to get any trend, you need at least 40 years worth of data because of this noise. Right? So if we can eliminate what's the causing of this noise as we model it out, we might be able to use 5 years worth of data to see what the trend is. So that's a bit of research waiting to be done to get a better indication of sea level rise in a shorter period of time. This is what it is in Texas, bigger and better. This is in Galveston, which is the longest record we have in Texas, and it's on the same datum still, 6.35 millimeters a year, which is amounts to, in English units, a little over 2 feet per century. So that actually makes a big difference when you're doing elevations along the coast. You really need, if you're going to build a building that's going to last 70 years, you might want to take that into account. Or any major bit of infrastructure like a port or an oil refinery, which there are a lot of in Texas. And they're building right now along the Texas coast liquid natural gas facilities to export natural gas. So they need to take that into account if they want to be around in 70 years or so, right next to the coast. So it's a problem. And so much so that nowadays we are putting GPS core stations on our tide gauges to measure the difference between the sea level rise and the subsidence. So the GPS observation will give us a direct measure of the subsidence rates. And this is you've probably all seen this before, this is the satellite altimetry data, which is measuring global sea level rise in mid-ocean, right? And so the data goes back to the early 90s, and this data trend is a little over 3 millimeters a year. So if you subtract that out of the tide gauge stuff, it gives you an indication of what the Earth's doing at that place. And on top of sea level rise, we get short-term sea level rise phenomena, which we call storm surges. And this is the storm surge along the New Jersey coast from hurricane or tropical storm Sandy. What do we do about these? And what do we do in Texas when we know the sea level's rising at things like rates like 6 millimeters a year? What are tropical storms on top of that? How is that going to predict what we do in the future? Or how can that help us plan for the future? So we had a a graduate student, a PhD student who graduated about 12 months ago. She looked at the long-term records for water level in Texas, particularly Galveston, because that was over 100 years worth of data, and picked out all the tropical storm surges in that huge 100-year data set and modeled them and came up with a statistical model which based on the frequency of the inundation and the height of the inundation. And it turns out to be a statistical plot called the generalized extreme value distribution. Now, I'm not a statistician, and me being a surveyor, and when I did the statistics of measurements, we use the bell curve, the normal distribution. That's the only distribution, statistical distribution that I thought existed when I was a surveyor. But there are other natural phenomena that plot for different graphs, and this is what's called the generalized extreme value. So if you plot all these storm surges over the last 100 years, this is the shape of the graph. And the most common is a little over a meter, 3 to 4 feet. And so you get the very high storms, the severe hurricanes, they're very rare. So there's not a lot of them. And we really don't worry about the very small ones. But this is the plot. And so if you extend this statistical model out into the future, and we're going out to 2100, if you look at that linear slope that I just showed you for Galveston, this is the ratio of the increase in the number of those storm surges in the next, until we get up to 2100. It's about, if you took the 95% level, it's about 11 times what we'll see today. So these 1 to 1.25 meter storm surges, we're going to see them at about 11 times what the rate we're seeing them today in 2100 relative to water levels today. So it's not going to be the long-term sea level rise that makes us change our habits along the coast. It's going to be the frequency of these little storm surges on top of the sea level rise that's going to change our habits. And this model over here is that if we use not just the linear graph that I showed you, but the accelerated sea level rise, which has been predicted by the International Panel for Climate Control, their middle of the road model, and you'll see it's up to 51 times. If that's what comes out at 2100, we're going to have 51 times the amount of inundation than we're seeing today with these tropical storm surges. So that's a problem to be dealt with in the future. We can use these models to help predict that. And so you've probably heard NOAA talk about coastal resiliency lately. So these are the problems that we're facing in terms of, this is in particularly Galveston in Texas. What are we going to do about that? And so there's schemes out there after Hurricane Ike. There's studies going on to look at building what's called the Ike Dike. And there's actually some Dutch consultants working on that right now. Whether it gets funded or not, that's another thing. So let me take you to our website to show you in a little bit more detail what the TCOM is all about. And this is a map of Texas, of course. This is the coast. And all the red flags here are tide gauges which belong to the National Ocean Service, which there's the Galveston one. Actually, there used to be two. There was another one called Galveston Pleasure Pier, but it was destroyed. No, it wasn't actually destroyed. The pier it was on was damaged during Hurricane Ike, and it was sold, and the new owners didn't want the tide gauge there, so it was removed. We replaced it with a new tide gauge in the Galveston Ship Channel, which is that blue one there. But the red ones belong to the National Ocean Service, and the blue ones belong to the state of Texas and part of the TCOM network. But we do include the NOAA gauges in our network. We do publish that data as well. And also NOAA publishes the data that we come up with from our network because we meet all their standards. And we're a partner with co-ops. And we've actually filled in a lot of the gaps which co-ops has identified for Texas in not having enough water level. So let me go to the and our data is actually available in nearly near real time. So if you hover over any of our stations, you'll come up with the latest set of observations. And just like the National Ocean Service, we have primary water level, we have a backup water level system, we observe air temperature, water temperature, wind speed, wind gusts. There's two lots of those. And here also the barometric pressure. One of the reasons why we capture all this data, not only because NOAA does, but one of the things that we've noticed in Texas, and we've noticed for a long time, that if you use the standard tidal coefficients, which helps us predict tides, if you use those coefficients to predict tides along the Texas coast, the actual water level matches the predicted value about 60% of the time. The rest of the time, the water level change is due to atmospheric effects, the wind speed, the wind direction, and the barometric pressure, because it's fairly shallow along the Texas coast. And most of the basin estuaries are really shallow, and it's fairly shallow several miles out. You know, you go out like 5 miles and it's still only like 60 feet deep. So the atmospheric effects have a big effect on the water level. And so collecting all this data, we have been using artificial neural network technology to train the software to identify the coefficients for wind speed and direction, and also forecast wind and barometric pressure, put that into the computation, and it comes up with coefficients to take those into account to predicting the water level. And so we can predict out the water level 12 hours and increase that match from 60% up to 90%. It's worse for 24 hours, and when you get to 48 hours, it's not very good at all. But for 12 hours, that's really good for shipping movements. And so if we got extra water, an extra foot of water for their ship channels, that's extra cargo that you can put on a ship, and it actually makes a big difference to them. So they, and the Weather Service knows about our forecasting, so we can better predict water levels so that the maritime operations are a lot more efficient. So that's one advantage of collecting all this data, and also using artificial neural network technology. So if we go to this station and click on it, there's a photograph of the station. The latest set of observations in both metric and English units and marine units. And this data is 6 minutes old. And this is the most recent observations for the last 24 hours, if you're interested in that. But if you're looking for downloading, and all our data is downloadable, and this is the historic data that we've been collecting since, I guess, about 1992, when this station went in. So we have primary water level and going back there. And so all this data is stored in our online in our servers. So anybody could come here and download any of this data going back to 1992. And we do keep track of our data downloads through Google Analytics. And we have about 5,000 people a day capturing our data. Is that much? And all over the world too, like places like Israel, Hungary, Australia. And one of the reasons for that is if you're interested in tides around the world, even if you go to England, you have to actually apply to get the data if you're looking for historic data. And then they'll say, what do you want it for? I mean, it's in the paper every day, but if you want like masses of it and get it in real time, they treat it as a strategic asset. Because going back to like the Spanish Armada, I think the reason why the British wiped them out is because they knew the tides a lot better. Something like that. But they, the Brits did figure out the tides and forecasting pretty much better. And so they view it, if you're going to attack England, which is an island, if you know what the tides are, you've got a better chance of pulling that off than if you don't know what the tides are. And a lot of countries have the same philosophy, even Australia does. It's really difficult to get long-term tide data in Australia, unless you like plot it every day from the newspaper. And so, but you know, America is a lot more open source with its data. You all know that NOAA gives it all away for free. And so do we. And actually our philosophy is the more people that use our data, the more useful the data is. And so we let it freely accessible to anybody who wants to use it. So you can download any of this data, and you can download it all. You can download it as a graph, or you can get the actual data points. So it's all 6-minute data. So you can get that going back to 92 if you want to. It's freely available. NOAA doesn't have this, I think as much as you can get from NOAA is about a year's worth of data, but all our data is online. Let's go to the forecasts. Okay, so this is our forecast for water level. The blue line is the harmonic predicted water level. The black crosses are what we actually observe. And we have two models, an artificial neural network, which is the orange one, and the green one is persistent. Persistent model is just moving the predicted model up to where the observation is right now. So right now the data is pretty well behaved, but we have, quite often we have the observed being like maybe a foot above what's predicted, or maybe a foot below what's predicted. So the data right now is actually performing pretty well with the predicted tides. When we get like cold fronts coming through or tropical storms, then it goes way out of whack. But that's the forecast predictor. And it does go out like 24 hours, but it's 12 hours is what's really good. But that's enough for coastal flooding warnings and also for ship movements. So that's the forecast data. So just like NOAA, we have a series of benchmarks around each gauge and a description of where the station is located. And so we publish, this is mainly for engineers and surveyors, we publish the elevations for each gauge, what the elevation of the water level datums on station datum, and what those datums are relative to each benchmark. So we have 1, 2, 3, 4, 5, 6 benchmarks at this gauge. And then below that is the descriptions of the benchmarks and where they're located relative to the gauge or relative to whatever buildings and street addresses are nearby. And we follow National Geodetic Survey with locating these. And the reason why we have so many benchmarks at each station is that it builds in redundancy in case they get destroyed. And that happens more than you'd think. Even in places like spoil islands, we've had benchmarks destroyed by barges. barges get out of control in Texas when they're empty and there's a lot of wind, and they end up running up on the spoil islands adjacent to the intercoastal waterway. So we've had benchmarks destroyed by barges. We have even had tide gauges destroyed by barges as well. This is a bob or pier gauge. This is a coastal, a Gulf of Mexico signal. This is on a pier that sticks out into the Gulf of Mexico. The data and
Why in the list of all of the datums do you not include something like the WGS-84 ellipsoid? Seems
Well,
like it'd be a useful thing.
well, that changes a lot. So what we publish it on NAVD-88, which is the official elevation datum for the United States, right? Now, the geoid is used to convert ellipsoid values, which you get from GPS, to NAVD-88. And that actually changes from whenever they do a new model, which has been quite frequently over the last 5 to 10 years.
Am I right in thinking that that changes NAVD-88 but doesn't necessarily change WGS-84?
Well, WGS-84 is the datum, right?
Yeah.
And so to get from that datum to a sea level value or NAVD-88 value, you need the geoid model to do that conversion, right? And that's assuming you're using a GPS, which is built into the software. And actually, if you're a surveyor, you should identify what geoid model you are using. So that's you get from the National Geodetic Survey. And NOAA, Co-ops doesn't publish that. So we do everything Co-ops does. But surveyors should and geodesists should know that, right? The public wouldn't know how to do that. But I get your point from a scientific point of view. You should be using the latest geoid model, which you get from the National Geodetic Survey.
Am I right in thinking that if you, like your NAVD-88 values aren't, you need to know what geoid was applied to get those, which version of NAVD-88?
Well, NAVD-88 is a fixed elevation based on sea level at farther point in the St. Lawrence Seaway, right? It was fixed in 1988. It hasn't changed. So, but the geoid model has changed since then. It's a fixed surface of the model of the Earth, which zero goes through mean sea level as it was in 1988 in the St. Lawrence Seaway at that point.
Okay.
And if you know that the 1929 adjustment of the elevations, it was tied to 26 tide gauges, including that one in Galveston. That's when they assumed that sea level was level everywhere. And since then we found out it's not. Sea level is actually locally at the tide gauge. It's different every point on the surface of the Earth. But and so what the adjustment in 1929, the tide gauges actually distorted the level network. You know, we didn't know much about geodesy and the geoid back then. And so they readjusted it in 1988 and they held the farther point tide gauge fixed because that was the one in the mean of the differences. So it made the least amount of change everywhere. And so that fixed the surface back then, which is a technically an ellipsoid surface that approximates sea level at farther point. And also, if you look at the contours with the difference between 29 and 88, the 0 wanders from Father Point down to central Texas. But even like, there's only like a very small part of the coast where it's 0, and as you move away from that, it just changes. The difference between sea level and NAVD88, well, we saw it just a little while ago. What is it here? It's taking a while to get this. Well, it's less than a foot, but it is measurable. The difference between sea level and NAVD88 at our tide gauges. And actually, the geoid is going to tell you the difference between sea level and the ellipsoid surface, right? I better not go there. We don't publish the NOAA station datums. We rely on NOAA to do that. Let's go back to Port Arandis.
To get to those, I think where you're trying to get to, and you mentioned you have a GPS campaign as well on these
Yes.
gauges,
Yes.
where a benchmark, a primary benchmark, would be occupied by a GPS station. So you'd be getting a time series of ellipsoid heights on a benchmark.
Correct.
So
Correct.
from that, you could relate your real-time water levels to a current ellipsoid height. So if you were, say, surveying to ellipsoid, you could tie that into real-time water levels
Right.
by that method.
Right, and sea level sometimes doesn't even match the geoid. I mean, the geoid's supposed to be sea level, but it doesn't match it everywhere. Okay, station data. So here we have NAVD88, and this tide gauge is 1.451 meters. And mean sea level is 1.639 meters. So there's a bit of a difference, like in feet. It's what is it? It's less than a foot, but it's measurable. Because that's this NAVD88 elevation is relative to sea level at Father Point in the St. Lawrence Seaway. And a lot of people don't understand that, including FEMA. One of the responsibilities of surveyors is what's called an elevation certificate. And so if you want to get flood insurance and you're near a floodplain, you have to prove that your lowest floor level is above the floodplain at that location. And surveyors have to fill out what's called an elevation certificate. And you have to put the datum that you're using for your survey, and the three choices are NGVD 29, NAVD 88, and other. Right? So on the Texas coast, if you're looking after your client, you put the NGVD 29 value because that's the lowest one, and gives you more freeboard. But the NAVD 88 is different. It's usually higher. But if you use other and use our tide gauges with the 2001 epoch, it's substantially higher. And so FEMA accepts all three. They don't understand the geodesy behind it, or the locals' mean sea level elevations. But it's an interesting point for surveys because in Texas, after Hurricane Ike, FEMA went in and remapped all the flood insurance rate maps. And of course the elevations rose because all these areas were flooded that were outside the original floodplain. So like in Galveston Bay, the cutoff elevation used to be 12 feet, now it's 15 feet. And so there's a lot of houses that are all built to the 12 feet. They're going to be in the floodplain, and their insurance rates are going to skyrocket like over the next 10 years because of this change in the way that they're funding flood insurance. The public doesn't know this yet. Yeah, and surveyors are going to get the blame because we're going to have to produce the elevation certificates.
You're the ones that caused the water level to change, aren't you?
Yeah, because we're just measuring it. We're not doing it. That's the way we look at it. So, I better get moving on. So that's in a nutshell what you can get out of our system. We have a lot of users, but the biggest users now are the public. And they use it to plan fishing and surfing and windsurfing and sailing events. So it's extremely good, and that's again part of our philosophy of the more people who use it, the more valuable it is. We're also getting into using the data, converting it into apps for phones. We have a wind app that gives you all the coastal winds. We have a transit app. If you're going along the Houston Ship Channel and you're a ship and you want to know what the clearance and the water level is going to be as you go along, it's predicted for you using NOAA's hydrodynamic model for Galveston Bay. So we're trying to invent new ways of and quick ways of extracting information out of this huge data set that we have, and kind of like what you guys are doing here as well. So let me move on to my rest of my presentation. And how Height Modernization ties into this. Back in 2012-13, we was some funded from the Corps of Engineers to tie all our tide gauges in, and a lot of their old historic benchmarks that they use for referencing their dredging operations, tie them all together with our tide gauges, and also including a bunch of the core station, the continuous operating reference stations, the GPS control points in Texas along the coastal areas. And so we used height mod observation techniques, which NGS put together, and used multi-station networks. We put in 72 networks, which involved a total of 153 stations we occupied. And we used their software called Adjust and Pages to do a multi-station adjustment of all the data. And then we blue booked all this stuff. If you know what that is, it's a formal process of getting the data from field to published in the national database for NGS. So we put this network of core stations, benchmarks, and tide gauges, and this is a fully homogeneous geodetic adjustment of all these GPS observations. And we did, each station was occupied for each network at least 48 hours of GPS observation. So it was a pretty rigorous campaign to tie all that elevation data together. And we've since gone on to do some more establishment of GPS on tide gauges. This is a new design. I don't know if you've seen these before. Co-ops designed this tide gauge as a result of Hurricane Katrina, and they built 4 of these, 3 in Louisiana and 1 in Mississippi after Hurricane Katrina. They cost NOAA about $600,000 a piece back in 2006. Since then, after Hurricane Ike, we put in 2 of these, which were funded by the Corps of Engineers, one in Texas Point, which is up here on the border of Louisiana and Texas, and one at Galveston, which replaced that Pier 21. And so we put core stations on top of these. That was also funded by the Corps of Engineers. And since then, we put in an extra 5 last year using Height Mod funding. That's the white ones, 1, 2, 3, 4, 5. And we've also have got funding from the CUP program, which is from federal oil and gas royalties, to build another 4 of these, and these are the white locations, and they're going in right now, and they will also have core stations on it. So we're using these huge superstructures to measure subsidence and sea level rise at the same time. And these are designed to withstand category 3, 4 hurricanes. And they're built this high because that's when Hurricane Ike at Rollover Pass, this is this white one. Yep, there. Our standard platform is about 14 feet, and it was overtopped by the storm surge at Rollover Pass for Hurricane Ike. So these went in about 2011, and they've withstood a couple of minor hurricanes that went into Louisiana since then. And these things stick out of the water around about 30 feet, and they go into the mud about 100 feet. And surprisingly, when they put the big pipe into the ground, about 70% goes in under its own weight. And then they hammer in the last 30 feet. So they're pretty substantial structures. But the price has come down since NOAA built the first ones. We're paying about $400,000 a piece for them. I think it's because the price of steel came down, and since 2008. So these are what we call Sentinels of the Coast, and Texas will have 6 come end of next year, and they will all have core stations. And another reason that we're putting these core stations on the tide gauges is the Corps of Engineers is really interested in using machine control, GPS-guided machine control, to monitor the dredging. And the Corps has also been forced to move to NOAA's water level datums to control all their dredging projects. Up until now, in Texas, they're using a datum which was established in like 1935 called mean low Gulf, which is about a foot below 1929 sea level. And so they're over dredging about 1.5 to 2 feet right now, based on that old datum, because they haven't taken into account sea level rise. And that was a problem in Katrina as well, by the way. New Orleans has subsided about 3 feet since 1929, and that was the datum that they used to construct all the levees. And so the design level is short 3 feet now than it was when it was built. So that was that problem. And this is why we have a need for accurate elevations along the coast. This is Houston after Tropical Storm Allison in 2001. It's a major flooding event. But it's not just the coast, it's the river systems as well. This is Austin in 1991, a huge storm. By the way, Texas has got some of the world's records for rainfall, especially in the hill country near Austin. They've had some fantastic storms up there where they've dumped more water in a short period of time than anywhere else on the planet. And it's from all this Gulf moisture hitting the fronts coming down from the north. Really serious flooding events in Texas. And actually Texas leads the nation in flood damage just every year, except 2005 when Louisiana beat us. And one of the reasons why elevations are so bad in Texas, and this is the NGS leveling observations which established the elevation control in Texas. They did the majority of the leveling back in the 1930s to 1950s. And actually NGS does not have a leveling crew anymore. And like the philosophy was back in the 70s, when they were starting to build the GPS system, that GPS was going to take over. But that's before they realised that they needed much better geoid models to help the GPS get to orthometric heights. And so they're working on that now. NGS has got a program called GravD, which they're observing airborne gravity observations over here. Not all the United States have come up with a much more accurate geoid model, which will give us hopefully centimetre accuracies and a definitive geoid which is accurate. And that'll be going to a dynamic height system rather than the static benchmark that we have from farther point. So, but this is the historic reason that all these established benchmarks were put in. They were put in roll roads that are now defunct, and also along highways which are now being destroyed because of widening. And it's estimated that the majority of the benchmarks that NGS established in Texas is probably about 20% left of them, because and a lot of them on the coast are subject to subsidence as well. So they're kind of out of date. And that was one of the reasons why Height Mod we even started, because a lot of the elevations that were established way back when, they've either disappeared or they've been subject to change. And so the Height Mod program is actually part of NOAA's budget, but it gets a total of $2.5 million a year to cover all the elevations in the United States, which is not enough. So that's the end of my presentation, and I'll be happy to answer any questions that you may have. 2 minutes. Yes, ma'am.
I'm just curious, those big new tidal gauges, are they going to measure the base height of the sediment surface at the top? So you could imagine that something that big, if it's there for 50 years, hopefully it lasts that long, it would start to sink, not just the subsidence of the ground around it, but the structure itself might start to subside.
Well, we're monitoring that. We level from the shore, we level to it at least once a year. And we also level the bottom of the, we have a benchmark on the boat landing.
Yeah.
And we have another benchmark up on the top landing. And we measure that difference using trigonometric leveling, but very precisely. We do it like 16 times around and connect it to other benchmarks using trigonometric leveling with really precise total stations. So we will monitor if it's sinking, and we'll adjust for that. But we haven't seen the others sink. The ones that we started in 2011, they haven't moved at all. So they should be fairly solid. But we're measuring the water level from the tide gauge 0 point down to the surface of the water. We're not worried about the depth of the water, as long as there's water there. Yes. And we're moving from an acoustic gauge to a radar system, a microwave radar system, which you don't need a stilling well, which is NOAA has blessed. So they're a lot more maintenance free. There's nothing in the water we have to maintain. Yes, sir.
Do you know if the data parameters, transformation parameters are compliant to your observations?
Yes.
Okay.
They used, when they did V-datum for Texas, they used all our tide gauges. Of course, we follow NOAA's standards. Yep.
And about the GPS network that you showed us, what is like the maximum length of those sites?
Well, I don't know. Maybe 30 kilometres, 50 kilometres, something like that. The adjustment, the pages and it does the adjustment. It's pretty rigorous, and like the tolerances were within fractions of a millimetre, you know, or just millimetres. It's well within geodetic standards in all 3 dimensions, not just elevation. Yep. And it's all blue booked. Well, actually, we have Height Mod partners in every Gulf state, and our Height Mod partner in Mississippi, it's a guy who works out of southern Mississippi State. They have a senator there that still believes in earmarks. And so he's created an earmark to cover not just Mississippi, but the whole Texas coast. So we're funding through that earmark, which comes through NOAA, through NGS. And this past year we've done the same thing with the tide gauges in Florida, connected them to cores and local benchmarks in the tide gauges. And that's about 80% complete now with the processing. And this year we're going to do between Louisiana and the western border of Louisiana and the eastern border, the western border of Louisiana and the eastern border of Alabama, filling in that with the network and adding more core stations to NOAA tide gauges. So we're doing it for all the Gulf Coast, tying in all the local mean sea level values to the network of core stations and benchmarks. But Louisiana is a special case because it's moving really fast. Like, one of the tide gauges in Louisiana, it's showing sea level rise of over 9 millimeters a year. It's really serious. So NOAA did actually, NGS did a big elevation campaign in Louisiana in 2006, straight after Hurricane Katrina, and they were out of date within 2 years. So it's moving all the time in the wrong direction. And that's another state where they over dredge. The Louisiana, so the New Orleans district of the Corps of Engineers uses a datum called mean low Gulf, which was established in 1916. So they're over dredging about 3 feet right now. But the Maritimers love it because they can overload their vessels and offload them in New Orleans.
Are other coastal states, like in the Atlantic and the Pacific, doing the same thing?
Not to the extent we are.
And why would they not be?
They're probably not as vertically challenged.
Yeah.
They've got more relief on the coast, like here. You know. Well, here you don't see much sea level rise. And I think it's the subsidence that's a big difference that we see down in Texas. California has some height mod issues because of earthquakes.
Yeah.
And they have a huge cores network in California, mainly set up to monitor ground movement, but also does the vertical as well. So they're kind of covered by the earthquake problem. Yeah. Yes, ma'am.
You said you were monitoring the subsidence
Yes.
that you were seeing. Do you have any results of that yet?
No, because we've only had GPS on tide gauges since 2011.
It'd be really interesting to see how much of that is.
Yeah, but if you just use the tide gauge record for Galveston, if you subtract the 3 millimeter global, it's about 3 millimeters a year.
So still over the average, or at average?
No, its total is 6 millimeters. So if you take out the global 3 millimeters, that means the subsidence is 3 as well. And so in Louisiana, it's 6 millimeters with the 3 millimeter sea level rise. So it's substantial. Yeah, Louisiana's sinking into the Gulf.
It's not very high.
No. There's a lot of communities that's been abandoned along the coast there.
They have, in South Louisiana, at least they did, and I don't know if it was run by the state or LSU, a course network
Yeah.
there, that's
Yeah.
been in place for some time.
LSU runs the cores network in Louisiana. And they fund it by charging surveyors a fee to use their real-time network. You can set up a core station so it broadcasts the differences from the actual coordinate to the observed coordinate, and which is applied in real time via the cell phone network to a surveyor in the field. And so they can get like centimetre accuracies up to like 6 kilometres away from the core station in real time. So, and they're willing to pay for that service, and so LSU is using the fees for that to keep the system running. Texas, on the other hand, it has a Department of Transportation runs the CORS network, and it's got about 130 stations. It's only available in real time to the Texas surveyor, TxDOT surveyors and their contractors, because they're private networks in Texas, and they don't want to compete with them, even though it's already paid for by tax dollars. And the other states like South Carolina and North Carolina, they have geodetics agencies within the state who run their CORS network, and they make them available for free. And some of the fastest users of that data is agriculture and precision farming. And so they love it in those states where it's free. It's not free in Texas. And maybe the farmers can actually lobby the state to turn it on. I would be if I was a farmer. It's all paid for. So, you're probably all anxious to go to the bar.
Thanks, everybody.